our goal today is to take a deeper look at distance and displacement. So recall that distance is a scalar and it is the total path taken. But displacement is a vector. And it is how far an object is from its starting position. And it has to include a direction. So the example we looked at kind of was here was point A and here was point B. And so if I take some wibbly wobbly path to point B and I measure the path length, that path length is the distance traveled. But my displacement, I'd have to actually draw a vector. The vector gets drawn directly from my starting position, directly to my ending position. And that would be my displacement, delta x. So that would be my vector delta x. So graphically, that's how I would represent it. To find that, I'd have to measure that length, and then the direction would maybe be to the right or east, depending on what coordinate system has been set up. So there are some rules for actually finding displacement. So we want to kind of look at that first before we look at some more examples. So when we are drawing displacement, here I used a different color, but especially if you're not using a different color, if say this was point A and this was point B, then when we draw our displacement vectors, we usually draw those as dashed arrows, because the dashed shows that there's a difference between my path, which would be a solid line, and my displacement, which I don't actually walk. So we tend to use dashed arrows for things in physics that is not actually what's happening. That's not what the motion actually is, but it's something that we are adding on to the diagram. So I would actually, if not using different colors, use that dashed arrow to represent the displacement. And then the magnitude is the length of that arrow. And the direction is where the arrow is pointing. So maybe to the right. So the magnitude is size, how long the arrow is, and the direction is where the arrow is pointing. And it always points from the starting point directly to the ending point. And all the way, make sure that the arrow actually starts on the starting point and ends over there. Now, we can calculate displacement if I have values. And as long as we are in one dimension, then our displacement delta x is going to be our ending position minus our starting position. So I'd have to know what those positions are within my coordinate system. But x2 would be my ending position. And x1 would be my starting position. So let's look at an example now that we've kind of refreshed our brains. So if I have an object is at the following positions. Along the x-axis. T equals 0 seconds. They are at a position of positive 1 meter. T equal 1 second. They are at a position of negative 1 meter. And at t equals 2 seconds, we are at a position of 0 meters. So remember, you should be making your T's curly like my T's are curly. They should not have straight sticks when you're drawing T for time, because that's going to be a variable. So we are going to start this problem by drawing a visual representation. Our goal is to find distance and displacement. So having that first visual is really important. Many of the first steps I'm going to have you do when solving problems will be to draw a picture. Not every time, but if I don't ask you to draw a picture and you're struggling, I suggest you draw a picture. So let's see. So here is our graph right there. We're going to use a number line because we're in one dimension. So I'm only going between +1 and -1. So I'm going to make this 0 and then 1 and 2 and -1 and -2. This is my positive x direction in meters. This is my negative x direction in meters. So what I'm going to do is I'm going to identify each of these points and kind of assign some variables to them. So at t equals 0 seconds, I am at a position of 1 meter. So I'm going to draw a dot here at +1 meter. And I'm going to call this position x0 and t0. The 0 represents at the very start. At t equals 0, t0 is 0 seconds, x0 is our +1 meter. So I'm going to use the subscript 0 to represent I'm looking at my very, very start at t equals 0. And then what happens is at 1 second, I have moved. So I'm no longer in the same spot. So at 1 second, I am over here at -1 meters. So I'm going to call that x1 is equal to -1 meter, and that is at t1 equal to 1 second. So once again, I'm using the subscript 1 to represent that this is like my next instant in time. It's my first motion. And then what's happened is going between position 0 and position 1, my start and this first point is I have moved, and I have moved to the left. So I'm drawing a little arrow there to represent that I have moved towards the left. And then after that, I still have one more motion. And that is at 2 seconds, I'm at 0 meters. So I'm going to put that here. So I'm going to define T2 to be 2 seconds and X2 to be 0 meters. And to get there, I had to move. And so, for example, we had to move towards the right. So those are the different motions that occurred. So now what we want to do is I don't even really need my setup anymore because my picture has all of the information on it. The first thing I want to do is I want to find the distance traveled throughout the whole motion. So if I think about actually I just want to do the first second. So I'm going to go find distance traveled from t equals 0 seconds to t equals 1 second. So from t equals 0 seconds, where I start off here at the purple point, and t equals 1 second, that motion is that orange arrow. So I can see that if I look here, that I have moved from 1 to -1. So that's actually a distance of 2 meters. So 1 to -1 is a distance of 2 meters. I went from 1 to 0 and then 0 to -1. So that is going to give me a distance equal to 2 meters. Now I want to find the displacement on that same interval. Find the displacement from t equals 0 seconds to t equal 1 second. So there's two different ways I can do it. I can just look at the vector I've already drawn and figure it out, or I can use the equation. We're going to practice with the equation. So our equation is delta x is equal to x2 minus x1. But I really don't like the 2 and the 1 because I've got a 0, 1, and a 2. Really, the 2 is just end and the 1 is means start. So I'm actually going to change those. And instead of using the x2, I'm going to use, and the x1, I'm ending at x1. So this one right here, this is x1 because that's my ending point. And then my starting point here is going to be x0. So I'm going to use x1 minus x0. I'm going to change those subscripts to match the scenario that I've drawn. And then I'm going to show my numbers plugged in. So x1 at t1, I'm at a position of -1 meters. Minus at x0, I'm at a position of +1 meters. So I'm going to show those exact substitutions into my equation. And I need my little meters there, forgot that. And I do -1 minus a -1 is a -2 meters. Or I could write that as 2 meters to the left. So I can see that since I went in a straight line to the left, my distance was 2 meters, and then my displacement was a -2 meters. So that kind of makes sense because I've just really added a direction on. So what we want to do now is we want to find the distance and displacement, not for that first section, but I actually want to do it for the whole motion. So I'm going to go back, and instead of going from t equals 0 to t equals 1 second, I'm going to repeat this, but I'm going to go to 2 seconds. So I'm going to find the distance traveled from t equals 0 seconds to t equals 2 seconds. And I'm going to find the displacement from t equals 0 seconds to t equals 2 seconds. So we already found that we went a distance of 2 meters to get from t equals 0 seconds to 1 second. But what I need to do is I actually need to go backwards, and I need to kind of go back towards where I started. So I went 2 meters to the left, and I'm now adding on 1 more meter. So for that black section, going all the way from the start, I'm going the distance of the orange, which I'm going to call like D1. And then I have to add on the distance traveled in the second section, which is the black section. So my overall distance, I guess I shouldn't use orange for that one. Let's use blue. So for that whole motion, oh, that wasn't blue. The orange section, I'm moving 2 meters. And then for that black section, I'm just moving 1 more meter. So when I add those up, my total distance is 3 meters. I'm going 2 meters to the left, and I'm going 1 meter to the right. So that's a total distance of 3 meters. Now my displacement is from the start to the end point. I can draw that as a vector here on my diagram. So to do that, what I do is I take my exact starting position, which I start here at 1 meter, and I want to draw an arrow directly from my start directly to my end. So I can add that here. And that is my displacement, delta x. from very start to very end. So my delta x here is going to be my ending position, which is actually x2 in this case. X2 is my ending position, minus my starting position, and my starting position is x0. So I'm going to do x2 minus x0. So end minus start. So my end position is 0 meters. I started at a positive 1 meter. 0 minus 1 is a negative 1 meter. So my displacement is negative 1 meters, or I can do 1 meter to the left because I ended up going 1 meter to left. And I can see that that matches my diagram. So my distance and my displacement are not always the same magnitude. They're only the same magnitude if I don't change directions. This is really, really, really important. Remember, magnitude is size. So if you move in one dimension, so basically along a straight line, without changing direction, then the magnitude of the displacement, so that would be like the number, is equal to the distance traveled. And the distance just has a magnitude. So in this case, if I go from position 0 and I go to position 1, that's that orange arrow moving to the left. My distance traveled was 2 meters. My displacement was negative 2 meters, or 2 meters to the left. The magnitude was 2 meters for both. But as soon as I changed directions and I compared the motion from the very start at the purple 1 meter to the very end, which was the blue at 0 meters, I only look at the motion directly towards for displacement. So my displacement was a negative 1 meter, even though my distance was 3 meters. So my distance and displacement no longer had the same magnitude, the same size, because I changed directions. So that's going to be an important difference. Another way you can write that is as soon as an object changes direction, the magnitude of the displacement is less than the distance, because your distance keeps getting bigger. So if I go in a straight line here, and then I come maybe at an angle like that, my distance keeps getting bigger. So I would add those sides of that triangle up. My displacement would be this line right here, directly from start, directly to end. So from geometry, you should know that the sides of a triangle always add up to a bigger number than the hypotenuse, or and this doesn't even have a hypotenuse, but just to the straight line. Okay, that's always going to be true. It's true for easier to see for a right triangle. But as soon as you change directions, the total path added up is going to be smaller. So that's really important. The last thing that we need to remember that comes as a consequence is that if an object ends where it starts, the displacement is 0. So let's say you are running laps and you start here and you're running around a track and you end exactly where you start. The distance traveled is 1/4 of a mile to go around a lap. But you end exactly where you start. So your displacement is 0 because you end where you start. Because your displacement is how far away you are from your starting position. So no matter what your path, if you end where you start, your displacement is 0. All right, so that's some things about distance and displacement.